All right, now the second video that you guys are going to see here is for part 2. And the part 2 video to this one is going to primarily be talking about not vectors that are in the full angle format, but they're going to be in what's referred to as a reference angle. And I'm going to even kind of like modify that. I'm going to say that they're in a bearing angle, and that bearing angle needs to be turned into a reference angle. Now, the reason why I teach both of these individual concepts is because you might run into two different kinds of questions. You're going to see a lot of bearing questions that are going to be in the worksheets for the next couple of days. So I think understanding how to do the reference one is important. It also is important in physics because they do all of their angles in a reference format. They don't do it in a full angle format. So it's important to understand that. Now, I'm not going to do number 5 first because I think number 5 is actually harder than number 6. So we're going to do 6 first and build our way up into number 5. Okay. Now, the rules to this are very, very similar in terms of a reference angle concept. The first idea here is definitely draw and I don't know why I put an R first, draw a pick first. Okay. Now you're going to start to see some information about a plane flying and it's at a specific miles per hour. Now that is a magnitude. We're talking about speed. You can think of velocities as magnitudes, but you're going to start understanding that you're going to start seeing directions. Now, due east is the direction of this particular vector. For instance, we're going to have to make sure you guys understand this is north, this is south, this is east, this is west. All right, let's get that in our brain first. Okay, some people have never looked at a compass, and you wouldn't believe they can't tell you which way east is. Okay, we got it now. East, that way. That's the way the plane's flying. Now to draw that actual vector, it would be going out in this direction at 400 miles per hour. Is how fast it's traveling. Now before we even go any further, I want to break down that vector V, into its component vector concepts. Vector V would actually be going in that direction, 400 cosine of, now you can even think of this as a full angle concept because it's on the actual axis at 0 degrees. This is cosine of 0, I, and 400 sine of 0, j. Now, the funny part about this is that these actually can break down relatively easily. This particular vector happens to turn out to be, if we take cosine of 0 is 1, so that means that it's going to be basically 400i. And if you take sine of 0, you get 0, and that would be 0j. Anything that's on an axis will actually be pretty easy to calculate. It's 400 going to the left, basically the idea. Now watch what happens when we do the next one, which is going, I believe, due north. 50 miles per hour due north is this little wind that's blowing like this. 50 miles per hour. I made it look smaller than the other one, so ultimately it's going in that direction. Now the question is where is the plane going to end up? If I did a little tip to tail right here, the plane should probably end up being pushed to a northern direction is where the resultant is going to actually be. Plane's going to be blown off course. Totally makes sense. Vector W, which is for the wind, is going to be 50 cosine of 90 degrees I plus 50 sine of 90 degrees J. Now if I evaluate that one, cosine of 90 is 0, so this would all become 0, and it becomes 0i. And this one would be positive 1, and 1 times 50 would be 50j. This is a really easy one to calculate, not really any need for a calculator to figure it out. Now the cool part is we can add those together relatively easily to get the resultant vector, which is 400i plus 50j. And then I would go on to that very last step after I've broken it down. So we would go to our components. That's the way we do next. Then 3, we sum them up and get the resultant vector. We do a little sum, get the resultant vector. And number 4, we find the magnitude and we find the direction. those are the two things we come up with at the end. Magnitude of the resultant vector would be the square root of a squared plus b squared, and the direction would be theta would equal the inverse tangent of b over a. Now, drawing a little picture here will help you recognize it is in the first quadrant, so I don't think we're going to have any problems with that. And if I put those in my calculator pretty easily, I'd get the square root of, let's see here, the square root of 400 squared, not 40, 400 squared plus 50 squared, and I would get a magnitude of 403 miles an hour. So it did get to go a little bit faster than 400 miles an hour. 403.11. Let's do that, miles per hour. Okay, and then the second one, and that's kind of a good reasoning right there to help you understand that, like, if you fly from Reno to Orlando to go see Disney World and you get a nice tailwind that's blowing the plane, that's why the plane can get there faster than flying you back from Orlando back to Reno, where it's blowing into the wind, because it's slowing the plane down. Yeah, now you understand that concept. The inverse tangent of b over a would be 50 divided by 400, and that answer would be in the second quadrant of a 7.12 degree angle is what's going on. Now, what is that angle really at? It's this angle that's listed right here, and that angle is a 7.2 degree angle being pushed in the northern direction. Now, this gives me a good opportunity to talk about bearings, because if you were in an airplane, you would take your bearings based on a compass heading, and that compass heading would be based on a north and south compass reading, because the actual compass points in the north or the south, depending on the hemisphere you're in. This would be the bearing angle on this side, and that would be a bearing angle, not the orange one that you found, which is 7.12. This would be north and going east, so this is a northeast bearing, and that bearing would be 7.12 degrees here, but this angle would be 90 minus that. And so I'm going to put here 90 minus the reference angle. And that angle would be, let's see what we got here, 90 minus this angle would be an angle of 82.9 degrees. 82.9 degrees east. And that would be the bearing way to write that angle. Okay? Now, understand the big difference here. This is a reference angle, because it's measured from the x-axis. This is a bearing angle, and a bearing angle is measured from north or south. It's off of the y-axis. Get those two straight, because we use reference angles to calculate vectors. We use bearing angles to tell you where you're going. All right, now let's go up here to number 5. That was a relatively easy vector problem. Now, the reason why I did that one is because in this one, the key is to find the magnitude and direction of the two vectors, but the vectors are written in bearings. And that's going to be the hardest part about these, is because you have to convert a bearing angle into a reference angle to make sure that you draw it correctly. Now, if I was going north 60 degrees to the east, I'm already focused on a northern direction, but I'm going to go 60 degrees to the eastern direction, and this would be the first vector at 75 newtons is where it's actually at. Now, before I even go any further, let's talk about this vector v and how I would write it. Now, this is a 60-degree angle right here, and the most common mistake people will do is they'll go 75 cosine, and they'll want to put a 60 right here. Now, that is wrong, because we don't use bearing angles to figure out how to do sines and cosines. We use the reference angle to figure out what that is. So you always have to use its complement when you figure these out. So instead of putting a 60, I'd put a 30-degree angle in there. I plus 75 sine of 30 degrees J. Now, this is a very easy place to make a mistake, okay? Don't make that mistake. The second is that once we use a reference angle, we have to pay attention to the signs of where it's at. If we're not careful, we won't know what the sign is. Since it's in the first quadrant, that is a positive quadrant, and that means that this should be a positive and positive concept, okay? You have to think about where you're at. Now, the second one, let me show you how this works on the second vector, is north 40 degrees west. North 40 degrees to the west is the way the second vector is being drawn at 90 newtons. Now, this is a 40-degree angle, but the reference angle that's associated with that guy is its complement, and that would be a 50-degree angle, and that's the one we need to use in our calculation. So if I want to do vector W, I would do 90 cosine of 50 degrees I and 90 sine of 50 degrees J. Now, before I go any further, I'm in the second quadrant, and that is negative positive, and that means this one has to be negative, and this one has to be positive. Now, you have to put those signs in, or you will get this wrong, and it'll be thinking that everything's in the first quadrant always. So you have to be thoughtful about your pick and what signs need to be on those, because these reference angles will always be smaller than 90 degrees, and they will always come out positive. So if you don't pay attention to the sign, nobody else will. Now, if I add those two vectors together, I should get a resultant vector of what's going on. Now, I'm going to pause the video right here. You guys calculate your resultant. I'll calculate it too as well, and we'll see if we come up with the same concept. All right, now I plugged those in, and I even alpha stored them too as well as A and B. But here's what I came up for as my resultant. 7.1 I, and the second one turned out to be, hold on a second, 106.44 plus 106.44 J. Now, the way I'm looking at these carefully, since both of these turned out to be positive, this resultant vector is in quadrant 1, is where it's actually located at. Now, since I stored those already as alpha A and alpha B's, I can calculate the magnitude and direction relatively quickly. But before I do so, I'm going to actually talk about one other word that actually is important here. Now, let me explain what's going to happen right here. If I said that this was going to be 7.1 and 106, it would be in the first quadrant. It would be over 6, 7, and up 106. So roughly the resultant vector would be something out there. Now that makes sense. If I tipped and tailed it, the blue one would attach here. It'd point out to this location. Here's your resultant. Now, what's going to happen is if these two vectors were actually working on this together, they would push that blue line or that resultant vector out to that location. But the question says it wants to produce an equilibrium. Now, if you see this word, what they're basically saying is, yeah, sure, those two vectors would definitely push that object in that direction. But if I wanted something to be in equilibrium, I would not want it to move. I would want it to stay still. So the question is what would I have to use as an opposite force to cause it to not move? Well, an opposite force would be a force that would go in absolutely the opposite direction, and that force would push it that way by that amount, and it would cause the object to be canceled out. Now, to make an equilibrium force, you want to make an opposite vector, and that's really easy to do with a resultant like this. A resultant equilibrium force, all you do to the resultant force is change its signs. If you change its signs like this, it just means that instead of going in the first quadrant, it's going in the third quadrant, and in the same amount in an opposite direction. This is the equilibrium force. That's why I called it resultant equilibrium. Okay, now, in terms of its magnitude, it would be exactly the same. So if I go in here to my calculator, and even though I use these same exact numbers, the resultant, the magnitude would be exactly the same. You would still calculate it with the magnitude of the resultant equilibrium force would still be the square root of a squared plus b squared. It still turns out to be exactly the same because it's the same size force. It's causing it to cancel out. So we would take the square root of alpha a squared plus alpha b squared and get a resultant vector magnitude of 106.7. That's what this is going to be. 106.7 newtons is what it is. Okay? That's your resultant equilibrium force. Now, the part you really got to pay attention to is that it really did change direction. So if I do the actual direction part of this, I'm going to get the inverse tangent of b over a. And be very careful. The thing it's going to give you is going to give you an answer that's in the first or the fourth. So it's totally not going to be the right one. It's in the third is where we really want it to be. And then you're going to have to think about the angle. So this is going to be something you got to really think about. The inverse tangent of angle alpha b divided by alpha a. And it's going to think it's in the first quadrant, but the equilibrium force, as you pointed out, is in the third. Now that's an 86-degree angle, is 86.1 is what it thought it was, and it thought that was this angle right here, 86.1 right there, but that's not it. That happens to be this angle right here, which is the same exact size, 86.1 degrees in that direction, in the third quadrant. Now, I don't want to do this as a full angle because if something starts out as a bearing, it has to end as a bearing. So what is the bearing angle right here that would be the bearing angle? Well, that 86.1 is this reference angle. The bearing angle would be southwest. So I'm going to go southwest. And how many degrees would that actually be? Well, it would be the complement of 86.1, and that answer would be 90 minus this answer, and that answer is a sliver of 3.81 degrees. 3.81 degrees. Ooh, it's messing it all up. Sorry about that. 3.81 degrees southwest. Okay? Bearing angle is complementary to the reference angle. So when you do your B over A concept, you always get a reference angle, and you want to take that reference angle and convert it into a bearing angle so that you can get what's going on. All right? Watch that again, because ultimately you do this several times, and it's super important that you understand that. Okay? Number 7 that's listed here about these two objects working as the angle that's in between the two. I'm going to go past this question because ultimately it's really should be drawn out like one angle is along here at 44 newtons. I would put it right along the x-axis, and the other one is a 40-degree angle working between the two as an 88 Newton deal. This is a 40-degree angle that's going on there. That's a reference angle right away. If I wanted to find the two individual vectors, they are relatively easy, and there's no need to use the law of cosines at all. Okay, you could put the other vector right here on the edge and use a 44 Newton vector right here and get the resultant, and then use the law of cosines like that. I don't know if that's really all that necessary, because we could write these two vectors relatively easy. Vector v, the 44 one, since it's going directly east, could be written as 44i plus 0j. That was pretty simple. And vector w is written as this guy going in this direction, so it'd be 88 88 cosine of 40 degrees I plus 88 sine of 40 degrees j, and you'd sum these two together to get the resultant vector magnitude and direction. Okay? I don't know. I think that's a relatively easy question. Practice it. See if you got that one under control. Okay? Number 8, really good question about, if you point your boat directly across the stream and you don't pay attention to the speed of the current, you're not going to make it to the ground where it's at. So you point your boat upstream and you end up finding a couple of things. Now the thing here that you want to pay attention to is the verbiage. You've got an angle that's in between the two. You can totally see that angle listed right here, okay? And where the vector ends up. This is the 25 degree angle that's going on in this vector concept. The other part is it says it's got 15 miles per hour for the speed of the boat. So that's a magnitude. This one's got a magnitude going down. That one's got a magnitude of going at that 25 degree angle relative to the ground. So think about those two vectors. And then it says, what is the vector represented at the boat compared to the ground? When you compare stuff to the ground, they want the resultant. Okay, that's what they're actually asking for, is what's the resultant of these two vectors. Well, the two vectors are basically v. Vector v is the boat, and that would be 15 miles per hour cosine of 25 degrees I plus 15 sine of 25 degrees j. There's your boat. Okay, it's going at a specific angle. The water, on the other hand, is pointed down. That's really super important. If you're pointed down, then that must mean that it doesn't have a vertical or a horizontal component, so it's 0I, but at the same time, it's going down, so it's got to be a negative 4j is what's going on right there, and we would add these two together and get the resultant vector. Okay, what's the speed of the boat to the nearest mile per hour relative to the ground? This one's asking for the speed, which is the magnitude, and this one is asking for the direction of the boat relative to the ground. That's theta. Those are basically the two things that you find once you've summed these two concepts up. You find a squared plus b squared and take the square root, and you take the b over a to come up with the angle. All right? So the question may be wordy, but the idea is that there's two basic vectors is what's going on, and that's how you calculate that. Okay? Now, this third day, I think that's a really good place for us to start for part 2. Maybe I'll even punch this guy out for you real quick and show you what you should come up with. So I'm going to pause the video here and show you what you should get. And you just saw me mess that up. Actually, I gotta fix this guy. This one should be about sine. Sorry about that. Messed that one up. See how it's easy, really easy to mess them up if you're not careful. So the two answers here should be 13.6I. 13.6I. So it looks like the actual current slowed the boat down. And then the second part is 2.33J. Now that's where the resultant ends up, okay, a little bit upstream of where he thought he was supposed to be. And now you could come up with the magnitude and the direction of that. And I like to do that whole storage thing because it makes it a little bit easier to type it in. And if you're careful about it and you keep it on there, you can actually go back and cut and paste this over and over again, and it makes it relatively easy to calculate. The magnitude of the boat, is at 13.8 miles per hour. Is how fast the boat is going, and the direction, since these are both positive, it's still in the first quadrant, so we should be just fine in terms of the angle. Let's talk about how that angle is going to be calculated here. So the inverse tangent of alpha b divided by alpha a, and that would be 9.63 degrees. 9.63 degrees. Now be careful. If that angle was measured from here, and it was measured from the ground, it'd be 9.63 degrees. I guess we could leave it like that because it was measured from the x-axis. If this question had been asking for what its bearing was, then you'd have to think about its complement, which would be northwest, and its northwest concept would be the complement of 9.63 degrees, or 90 minus this, which is 80.23 degrees, or 80.2 degrees west. That's what the bearing would be. All right? Okay, get the idea. When you do your inverse tangent, you're getting a reference angle, and a picture is really worth all of it, is really what's going on. Okay? All right, that'll get me done with part 2. Part 3, I'm going to break this up into a third part because these last 2 problems are a little dicey, and you want to have some extra time to really think about them.